In learning objective B, we're going to prove algebraically if functions have certain types of symmetry or if they're even and odd. So let's first look at this example here. And what you want to look at in particular is this parabola here over to the left. If we look at this ordered pair that sits on the parabola, they call xy. Let's call it 2, 4. Because remember the equation of the parabola, by the way, of a parent is y equals x squared. So 2, 4 would sit on it. Well, if you take that right-hand side of the parabola, and if you flip over the y-axis, what's going to happen is that ordered pair is going to go here and become the ordered pair negative 2, 4. So the relationship we see happening is letter A here. The y values stay the same, but the x value is the opposite. So in order to mathematically prove if something reflects over the y-axis, all you have to do is you put negative x into your equation. And if you do that, if you come back with the same equation that we originally had, then it means it reflects over the y-axis. So let me show you. With this particular equation here, let's just take a look at the graph. So it's roughly going to look something of this shape, where this side here will be the mirror image of this side here. So it looks like it does flip over the y-axis. Well, to prove it, you come into the equation, and we're going to put negative x into here, simplify, and if we get the same equation back, proves that this thing will reflect over the y-axis. So I'm going to find f of negative x, which means just put negative x in the original x value. We're going to square it plus 1. So we have 1 over, well, negative x times negative x is a positive x squared plus 1. Well, this is what the equation looks like in its final state, which looks like the original function. Therefore, we know that this does have symmetry with respect to the y-axis. Now, you're not going to have to mathematically prove if something has symmetry with the x-axis, but let me show you what that would look like. If we take a look at this function over here, with the x-axis is right there. Well, let's pick an ordered pair that sits on this graph, and let's call this ordered pair maybe 2, 2. Well, if you flip over the x-axis, what's going to happen is the x value stays the same, but the y value is going to become a negative 2. So in this case, the x stays the same, but the y becomes negative. Again, we're not going to prove it, but do understand what the graphical relationship looks like if you flip over the x-axis. Now, you are going to have to prove if something is symmetric with the origin in that it has rotational symmetry within 180 degrees. Well, if we look here at this function right here, it looks like it could be possibly a y equals x cubed, but I'm not sure. The origin is right here, so if we hold our finger steady on the origin and spin this graph and rotate it that way, it will end up looking like itself in 180 degrees. Well, what happens to the ordered pair? Again, let's say this is the ordered pair 2, 2. Well, if we rotate it this way until we get over to this spot, it'll actually become negative 2 and negative 2. So we see the letter C relationship, which says if we put into the function a negative x value, what we get back is the opposite of the original. So they want us up here to prove that y equals x cubed is symmetric to the origin. Well, first thing I would do is put this in your graphing calculator, and it will look something like this. And it seems reasonable to say that this thing will rotate at the origin, and if you rotate within 180 degrees, it'll look like the exact same graph. So what they're saying is, let's put a negative x in. Now, we have to get the opposite of the original function is what negative y means. So they're saying when we're done, it should look like not y equals x cubed, but y equals negative x cubed. So this test is saying, all right, do it and see if we get that back. All right, so I'm going to do f of negative x. If I put negative x into the graph and cube it, that'll be negative x times a negative x times a negative x. Well, there's 3 x's, but the 3 negatives will still make it negative. So the answer here is negative x cubed. And that's what the math comes back to be. Well, that's exactly opposite of what the original equation was, which therefore proves this rotates around the origin. Now this is an interesting question. They have part of the graph already here, and it's x times y equals 12. Now, if you were going to put this in your graphing calculator, what you would do is get y by itself, so you would just divide by x. So really this is the equation y equals 12 over x. If you graph that, what you're going to see is there's more to this graph. This is the first part in quadrant 1, but quadrant 3 also has this image. And they want you to look at it and you can see what type of symmetry it has, and then we can actually prove it too. Well, here if you hold steady at the origin and you take what's in quadrant 1 and rotate it 180 degrees, it will land on the same part of the graph. So it does have a rotational symmetry at the origin, which means if you put a negative x in here, we'll just take, this is our original equation, because that's how we typed it in the calculator. That's the original. If we put a negative into there, it'll be 12 divided by negative x. Well, there's nothing to simplify. That's what it looks like. So they're saying, well, wait a second, this is the original graph. If it rotates at the origin, the opposite of the original graph should happen, which would be negative of that. Well, negative 12 over x is the same as 12 over negative x, because you can move the negative to the bottom of the fraction if you want. So this mathematically proves it rotates at the origin. Now, there's a specific vocabulary word for both rotating at the origin and reflecting over the y-axis. It's even and odd. So what they're going to tell us is if we have functions that are the format of x to the n power, and we're looking at n's greater than 2, so we mean something like this. What if we have x squared, x cubed, x to the 4th, x to the 5th? Typically, if n is an even number, it could be symmetric to the y-axis, which means we call it actually an even function because of the exponent. Well, if the exponent here instead isn't a 2, but it's a 3, a 5, or a 7, that's an odd power. So it tends to be, it says symmetric here, change it to symmetric to the origin. So it'll have rotational symmetry, and we call that an odd function. Now be careful, just because if someone gives you this equation right here, y equals x cubed plus 1, if you look at the exponent, you think, oh, it's an odd exponent, I'm going to say it's an odd function. Not necessarily. It actually has to rotate just at the origin, so we do have to check it. And we briefly already talked about this. Remember when we checked to see if something flipped over the y-axis, we said let's put a negative x into the graph, and if we do and we get the original graph back, then we call it reflective over the y. Well, the technical word for that is we call it even. So we're really doing the seeing if it flips over the y-axis test for this one right here. Similarly, for an odd function, which we talked about, it just said here if we put a negative x in and we get back the opposite of our original graph is what that says, then we actually call that odd. And this just means it rotates around the origin. So what you want to come away from on this slide is what we did for reflecting over the y-axis is the same test that you do for an even, and this is how it formally looks. Also, if it rotates around the origin, that's the same test to see if a function is odd, and this is the mathematical kind of f of x function format for that. So now I just want you to make note of this slide. I think it's a great summary reference as you're doing your homework. Here it says if something is symmetric over the y-axis, again, we're going to see the ordered pair relationship. Let's jot this down. We call it even, and the test again is f of negative x. When we put the negative in, we get back the original. Now this second one again was just more informational, what it looked like to flip over the x. The last test we did, is it symmetric to the origin? That is, does it rotate at the origin? This one here is going to be our test for being odd. And on that, we're going to put a negative x into the function. And if we get back the opposite of the original function, then we would say it's odd or it rotates at the origin. Let's look at two examples. Here's the first one. And what I recommend you do is actually graph these to get a gut feeling of what the answer should be. Now, make note of this kind of weird notation. This is f of x equals or y equals. It's just another way that the book will do this. So f of x equals means that, or y equals means that. It's just this right here. And let's put that in the graphing calculator. Okay, this is a rough sketch of it, but if you look at this function, the first thing I'm going to do is notice the highest exponent is an odd power. So I'm wondering if it's the odd power. If it's odd, which means it rotates at the origin. So the origin is here. So if we hold our finger steady there and rotate it, within an 180 degrees, this graph will look identical to itself. So I suspect the math's going to kick back and say it's odd. So here's what the test is going to say. Again, we are given this is the function. And what we're going to do is we're going to put in a negative x. Before we do that, I'm going to go back up here and write what would the opposite of f of x look like? Well, the opposite of f of x would mean change the sign of this and this. So this would be a negative 4x, and this would be a plus 2x cubed. Now, once you do your test, if your final answer that we get down here, if it comes back and matches this one, then that would be even. If it comes back and matches this one, it's odd. If it doesn't match either one of the two, then it's neither. So let's do the test. I'm going to put the negative x into here and here on the function. So that's going to give us 4 negative x minus 2 times negative x cubed. 4 times negative x is negative 4x. We have negative 2, or minus the 2. Negative x 3 times is going to be a negative x cubed. So this is actually a little bit different than this. I actually wrote this out 3 times and simplified it to here. Now if we finish our simplification, it's negative 4x. A negative 2 and negative x cubed is plus 2x cubed. So this is what I'm looking at as our simplified function. And when you notice that, you're going to see that this is identical to what we thought it should be for odd. Therefore, we just proved algebraically that this function is odd. Okay, let's take a look at another one. Now, the highest power on here is a 2, so it's an even power, so I'm thinking it's an even function. An even function means that you would flip over the y-axis. So again, let's just graph this first to get a visual. Okay, so this is what the graph looks like. And it actually is close to looking like it flips over the y-axis, but it's moved over actually a little bit, and it doesn't flip over the y-axis, it doesn't look like, because if it did, what I'd have to do is this part right here I'd have to take, and I'd flip over the other side, and if I did that, I'd get like this W-looking shaped graph. Well, that's not what the red graph looked like. So to me, I'm guessing we're going to come back that it's neither. And here's what I'm looking for. When I put the negative x in, if it comes back again to be the original, then that would say even. If when I put the negative x in, I get the opposite of it, so everything changes. So that would be a negative sign. This would be a plus sign. Then it would be odd. If I get a combination thereof, where it's like negative and negative, then it's neither. So let's do the test. I'm going to put a negative x in. We get 3 times negative x squared minus negative x. Okay. Negative x squared is going to be x squared. Negative and negative is plus x. And then this right here will simplify to 3x squared plus x. Now when you look at that, it has to have a plus 3x squared and a plus x. This has a negative and a plus, this has a plus and a negative. So this tells me that it's neither. But again, when I graphed it, I could tell it didn't look exactly proper. You know, in conclusion, this here is another fabulous quick reference slide where it talks about if it's an even function that we see it over the y-axis. Here's what happens to the ordered pairs. Here's what the test kicks back, and then you have a nice visual representation. Likewise, the odd function does that too. It's symmetric about the origin, the ordered pairs. The test comes back like this. And here's a nice visual representation. The one thing you need to be very careful about for even and odd, though, is even is very specific. It must just flip over the y-axis. If you have a parabola over here, yes, it has symmetry. That symmetry is on this line. It's not the y-axis. It's not even. With an odd function, it must rotate at the origin. If this graph was over here and it rotated at this point, that's not the origin, it's not odd. So it is very specific on where the even and odd happens. So remember, the two green graphs here are either not, this is not even, and this other one is not odd.